Let's go ahead and get started. And so welcome. Hello, everyone, and welcome to the September NASA Night Sky Network member webinar. We're hosting tonight's webinar, as usual, from the Astronomical Society of the Pacific in San Francisco, California. We're very excited to welcome our guest speaker, Dr. Erwan Mazarico from NASA's Goddard Space Flight Center, and he's also joined by Andrea Jones, who is a frequent guest here on these webinars. Before we introduce Dr. Mazarico and Andrea, here's Vivian White with just a couple of announcements.
I'll keep it quick. I even brought slides this time. I want to encourage those of you on Zoom to stick around for the very end to help us with the survey and enter to receive a signed copy of our friend Robert Reeves' brand new book, just came out this week, Exploring the Moon with Robert Reeves. Many of you know and love him, and I'm sure he needs no introduction. One other quick announcement. We just pulled all of the events that were happening for the annular eclipse on October 14th, and any club who has an event listed, be they public or private, on October 14th should hopefully be listed here, because we are sending you big boxes of eclipse supplies. So glasses and posters and postcards and golly, anything you might want coming to you in a box. Those are being sent out this week. So if your club is on here, keep an eye out for a box. And if your club is not on here and you think it should be, send us an email. Those are clubs that have events posted on October 14th for the eclipse. These eclipse boxes will also have some great things from International Observe the Moon Night, which happens just a week later. We're going to hear all about. So I wanted to encourage you. I'm going to leave this one up and turn it back over to Brian. But one quick thing, if you need anything and you think your club name should be on here, send us an email at nightskyinfo@astrosociety.org. And I bet Kat can throw that in the chat. Thank you so much. And if you are going to plan an event, you forgot to put it up there, you can also shoot us an email if you do it in the next day or two. Thanks.
All right. Thank you, Vivian. So as usual, for those of you on Zoom, you can find the chat window and a Q&A window at the bottom edge of the Zoom window on your desktop. Please feel free to greet each other in the chat window, or to let us know if you're having any technical difficulties, or if we prompt you to, put something in there. We love to hear things from all of you. You can also send us an email at nightskyinfo@astrosociety.org. If you have a question you would like our guest speaker to answer, please type it into the Q&A window. It's the Q&A window that really helps us keep track and know if we have answered your questions or not. A lot of times we get similar questions and things that we can follow up on. And if you put all of those into the Q&A window, it makes life a whole lot easier for all of us. So let me, where did it get to? There it is. Again, welcome to the September NASA Night Sky Network webinar. This evening, we welcome Dr. Erwan Mazarico to our webinar. And here's Andrea Jones with a quick message about International Observe the Moon Night and to introduce our speaker. Andrea.
Well, thank you, Brian. Thank you, everyone, for coming. Thank you to the whole Night Sky Network for joining us. It is a pleasure to be here with you again. I love coming to your webinars. They're so much fun, and there's so much energy and so many ideas that come through the group. So it's really wonderful to be able to join you. And tonight, I'm telling you a little bit, in case you're not aware, International Observe the Moon Night is coming right up. So it's on October 21st, 2023. This is a day each year when we invite everyone on Earth to observe the moon, to learn about the moon, and to celebrate the moon and our personal and our cultural connections to the moon. It is coming 1 week after the annular solar eclipse this year. We actually have some special products in honor of that. So we have a moon observation journal where you can start your observing on October 14th and continue through International Observe the Moon Night and beyond, that we're going to be handing out at our eclipse events. And we're really also excited because this is a time each year that we try to help people understand what's been going on in lunar science and exploration. So we can't do all of that in one place. We actually have a collection of lots of lunar science highlights that we're going to be sharing on our website, moon.nasa.gov/observe. But we wanted to have somebody come and give you a glimpse into the amazing things that have been going on this past year. And so it is a great pleasure to have Dr. Erwan Mazarico here with us tonight. I heard Erwan present at the Artemis science team meeting a few months ago, and one of the heads of Artemis Science, so Artemis, of course, is our return to the moon with humans, with people, and with commercial entities, with universities, with partners around the entire planet, getting people back to the moon. And he was talking to this science team about the incredible lighting conditions at the lunar South Pole. And he was introduced as the world expert on this topic by the Artemis science lead. And it was so cool. And I thought, lighting, the shadows, the brightness, the areas that we have on the moon, this is why we see it on International Observe the Moon Night and every night. And I thought it would make a nice hook to talk about, the lighting conditions at the South Pole as we're preparing to go. And Erwan is amazing. He's got so much cool stuff going on, and I'm really excited that he is here with us tonight. And I hope you all enjoy his presentation. So thank you, Erwan.
Okay, great. Well, thanks, Andrea, and thanks to the whole Night Sky Network for the invitation. I'm quite excited to be able to share with you some what I do, but also more generally some what NASA is doing now and has been doing. So as Andrea said, today I'm going to talk about exploring the shadows at the lunar South Pole, and you'll see why this phrasing is important. So I'm going to start with talking a little bit about the Artemis program, because that's a big reason for doing some of this work, and also, as Andrea said, for a lot of excitement, both in the science community and in public at large for all that's going on with NASA and the moon. So here's some mission statements from NASA. But really, what's exciting, especially for me, who was born after the Apollo era, is to see really humans back at the moon and be able to do science and explore a completely new region on the moon. Also, as Andrea mentioned, there is a lot of it's a lot broader effort to try to get to a long-term sustained exploration. So that makes it quite exciting, with first people on the moon and eventually to Mars. As you may know, and I'm guessing this audience is more tuned into what NASA has been doing recently. Last year, we had the launch of the Artemis 1 mission, which is the first test of the SLR system to be able to launch the Orion capsule and bring people to lunar orbit. And so that was a very successful test. And coming up very soon, we have the Artemis 2 crew mission. And so that will be the first time since 1972 that humans have traveled past the low Earth orbit. So this is coming up quite soon. The crew has actually been announced a few months ago. And so here you can see them, American and Canadian crew. And so, they're working hard, getting ready for this mission. And I'm sure there's a lot of excitement all around the world for this. Of course, they won't land on the moon this week. It's going to be more like a flyby of the moon. And it's only Artemis 3 that will go and actually put people down on the ground. Again, very exciting, more than 50 years after Apollo, that will be a huge milestone. And the South Pole region is, quite different from the Apollo locations, as I'm going to discuss a little bit more. So we already sort of know a little bit where Artemis 3 is going to happen. NASA last year down selected to 13 regions around the South Pole. You can see here from the blue lines, those are the longitude and latitude lines around the South Pole. So you see the South Pole is right there in the center on the rim of Shackleton crater. And those squares show the sort of generally 15 to 20 kilometer wide regions that have been selected for a number of reasons, both scientific interest, safety, but also orbital dynamics, all kinds of reasons that made us basically hone into those. And so I'm going to talk to a couple of those factors that enter that, both the scientific interest in terms of the colder regions and the volatiles that we may find there, and also in terms of long-term sustained exploration, why those regions are also of interest. So, first, why is the South Pole of the moon different from the rest of the moon? it's actually, I know recently, a few months ago, Brian Day gave a presentation that was focused on some of the Apollo landing sites. And this video from the Science Visualization Studio shows you in sort of, sped up time with the correct optical aspect of how the moon looked from Earth, how the exploration of the Apollo era occurred. And so you can see that Apollo 11 and 12 were very close to the equator, and the rest of the missions are also in a pretty close equatorial band. And so out there, obviously, the moon has about a 28-day cycle. And so you have 14 days of day, 14 days of night. And those missions only lasted a few days to be able to take advantage of optimal lighting conditions. And also, given this is a lot of astronomy club sort of audience, you know that the librations, the sort of wobbling and rocking back and forth of the moon here is primarily due to the moon's orbit, inclination, and eccentricity. And in reality, the sun doesn't move much up and down along the equator. So again, just a quick reminder that the seasons on the Earth and on the moon occur because of the actual tilt, the polar tilt, and that in certain conditions, you can actually have polar nights, right, where the sun doesn't rise above the horizon for many days, and polar day when the sun doesn't go below the horizon for many days. And so that occurs on Earth at specific latitudes. And on the moon, this is also what drives a lot of the peculiarities of the South Pole and the North Pole. And so this was recognized actually pretty early in the 1950s, that because the spin axis of the moon is only tilted by 1.5 degrees compared to the sun direction, any deep cavities, any deep depressions close to the pole would actually provide shading throughout the year, right? And so here you can see from this graphic at the bottom, very simply from the two opposite directions, when you have the summer solstice, so when the sun is highest in the sky, at midnight, when the sun is on one side, the rays only reach down to, let me put the laser pointer, only reach down to this. So, everything else here is shaded. When it's on the opposite side, the sun only reaches down to that part of the slope of the crater. And so this whole area in black actually never sees the sun during the year. And because the moon orbit has been very stable for billions of years, this means that those regions have been dark and cold for billions of years as well. So the big question is, is there ice down there? Are there volatiles? And that's of a lot of scientific interest in terms of delivery of volatiles throughout the solar system, but also for exploration. So coming back to Apollo, one thing when you look at these images is that you see that the moon looks obviously very different from the Earth, but in terms of the shadows, you can see here, the shadows are pretty small. The sun was basically almost at noon. And also when you look at the antenna, you see the Earth also was very high in the sky. And so this provided, sort of easy conditions to work in for the astronauts. This picture from Apollo 17 was actually pretty difficult to take because the Earth was so high in the sky that Gene Cernan, taking the photo of Jack Schmitt here, had to do some moon acrobatics to be able to fit everybody, the astronaut, the flag, and the Earth in the frame. When you zoom in actually to the helmet here, you can see that he's crouching and trying not to fall down while taking the picture. And so this is just to illustrate a little bit that the sun, the Earth travel in a sort of usual path of going from the morning, going high at noon, and going low again in the evening. And so this video that was made also by the SVS studio at Goddard shows you what a day looks like at different latitudes on the moon. So the top two are Apollo sites, 9 degrees south, 26 degrees north. And the bottom are regions actually we haven't explored yet, so 60 degrees north and 90 degrees south. And so you can see that during the day at the top, and even at 60, you can see that the whole surface seems mostly illuminated, and the whole surface becomes pretty bright. And close to evening and morning, there are pockets of shadow, regions that are more shadow than others. Let me rerun that. But you can see that this is sort of a typical day. Whereas on the bottom right, if you focus on that now, you can see that the sun direction basically stays at the same exact height. And the sun seems just to be circling around you nonstop. And you can see that the shadows are a lot more complex and sweeping through that. And so that offers a lot more complexity and seemingly chaos a little bit in there. And so that creates areas that are, seem never to see the sun, some areas that have very complex times of illumination, not just from morning to evening, but some of them are illuminated at local midnight, but not at local noon. Things like this that are quite complex. So the South Pole region and the North Pole are definitely very different from everything we've seen with Apollo, and that makes it exciting and very new. Also, if you were standing here at the South Pole, looking towards the near side, so looking towards the Earth, you see that the Earth is moving along different arcs, but pretty slowly, and only going up and down by about 7 degrees from the horizon. You can see that the shadows around you can be pretty extensive, and that the sun always stays very close to that line of topography. And so here again, you see the Earth go up, and pretty soon it's going to start going down again. And so all of those are very alien sort of conditions of lighting and of where the Earth is. If I can let the movie run a little bit longer, you'll see actually an eclipse where the sun goes behind the Earth. Those are a lot more frequent at the moon than on the surface of the Earth. So let me just wait a second for that. Yeah, that's what's happening now. So maybe the astronauts will be there at that time, and that would be a very, very cool observation that nobody's ever seen before. So also having a low sun actually is bringing some glare issues potentially, and we have some experience with that from Apollo 12, where this EVA-1 had the lowest sun elevation of any surface mission from Apollo, and you'll note that the elevation of the sun was about 8 to 9 degrees during that traverse. And when the astronaut looked directly at the sun, right, that image on the right shows you that it was, it made it a little difficult to see exactly what you were doing. So this is something that, people are working on and considering. And in the Artemis zone, which is that 84 to 90 degrees south region, so that pretty extensive region around the pole, the maximum declination of the sun would actually be 7.5 degrees. So instead of the best conditions, we'll see something similar to this. So it's definitely something that is going to make everything look also different for the people on the ground. So as I mentioned a little bit, there are two big reasons, I think, for why the South Pole of the Moon is of very high interest and put the South Pole of the Moon squarely in the planning of Artemis. One is the cold trap volatiles, and I'll go through that in quite some detail. So both scientific interests, as I mentioned, and exploration interests. And the exploration interest, I won't talk too much about here, but basically the point is that if you can find ice or other volatiles in situ, then you can maybe use them to build, to make rocket fuel or other resources to be able to use them. And that will significantly reduce the cost of bringing or using hardware on the moon, and also make that more sustainable. So this is, for the long-term exploration, the sustained presence on the moon, this is also a big interest. And then the other one is sunlight itself as a resource. I showed you that some of the lighting conditions can be quite challenging at the moon, at the South Pole, but I'll show you that actually it can also be an advantage in some very special places. So first, where is the polar ice, right? You may have heard that there is water on the moon, and so the moon minerals themselves hold some water, but this is pretty hard to extract and in small quantities. And so based on this idea from the 50s that there is permanent shadow in the craters at the poles of the moon, ice may have been delivered there over billions of years, and so it may have accumulated and be stable. And so maybe we can go and find it. And so the idea early on was to use ground-based radar, like Arecibo and other facilities, to look for anomalous signatures in the radar returns. And that was done, but no signal was really detected. Nothing, no smoking gun was found. And so potentially it's because the ice is not very pure, and the radar is very sensitive to nearly pure ice. But once you mix it up, or if it's depending on the grain size, it could maybe hide the signature. also looking at the radar data at the resolution of tens of meters to hundreds of meters, there was no unusual morphologies that were found within the polar craters that could be seen. Some of the polar region was hidden because some of it can never be seen from the Earth, but a large part of some of the big polar craters could be seen, and there was no telltale morphology like you could see on glaciers on Earth or something like this. So, and that was in contrast in the 90s to data was coming from Arecibo itself about Mercury's polar regions. Here on the right, you can see one of the images that was sort of summing up many observations of Mercury North Pole. And you can see there that the polar craters really light up, and that's indicative of nearly pure ice in the top meter or even at the surface of those craters. So those measurements were confirmed by MESSENGER, the mission that went to orbit Mercury, confirmed that there were cool temperatures, confirmed there was ice and bright material on the surface. But also it found actually a more complex story where maybe even organics are present within those craters. And despite this complexity, the whole story about volatiles at Mercury currently seems to mostly make sense and hold together. On the moon, it's actually, there's still an active area of research. There's still a lot of questions about, where is the ice? What's the nature of it? How deep is it? All that is actually very complex. So, and it's very complex in part because we have many different instruments that have looked at the moon and have had inferences that are compatible with ice, but they don't all correlate well with each other and don't necessarily agree with each other. And so that's also a reason why scientists are quite excited about Artemis going to the South Pole, because that will give us really, ground truth, and specific experiments can be designed to re-answer the conundrum that we are in some way. So in the late 90s, the Lunar Prospector mission was, stayed in orbit around the moon for about a year and a half at low altitude, and it carried on board a neutron spectrometer. And that neutron spectrometer in part measured what are called the epithermal neutrons. So when you have a galactic cosmic rays that coming from the galaxy and impact the moon surface, at some point it will hit some atoms and scatter, and they will make a whole range of products. And that's indicative of the composition of the ground. And so that's why it's very interesting. So you have both neutron spectrometers, but also gamma ray spectrometers. And so sometimes those go together in the same package, but not always. And so gamma ray typically show you, higher atomic weight elements, where the thermal neutrons and epithermal neutrons are indicative of objects that have, of atoms that have pretty large cross section compared to neutrons. And so that's hydrogen. So when you have a deficit of hydrogen, typically that means that there's a lot of absorbers or things that can modulate the neutrons that come out of that interaction of the galactic cosmic ray. And so that's exactly what Lunar Prospector found. They found that when they were close to the poles, the count rate of epithermal neutron was going down. And specifically when they mapped that on the ground, they could see certain areas at really strong deficits. And so those were thought to indicate the presence of ice. But because of the resolution of the instrument, it just measures, the whole sky that is visible. So there is not really like any pointing resolution. Because of that, the spatial resolution of that measurement is, several, maybe 50 to 100 kilometers. And so that could not tie directly one-to-one a deficit of neutron, which is thought to be ice, to a specific cold trap or crater. And so, but that was a very strong evidence that there must be a lot of hydrogen in some locations in the south pole of the moon. And because of the thought of cold trapping and those cold craters, this sort of, led to a lot more investigation into volatiles at the poles. And so in part, some of the instruments on the LO spacecraft, which launched in 2009 and is still operating, brought new data sets that could answer with different measurements. And so, a little bit in different directions, the question of the polar environment. So one of the ones that I'm more familiar with, because I worked a lot with that data, that instrument, is the Lunar Orbital Laser Altimeter, or LOLA. And LOLA measured the topography on the elevation of the moon, the relief of the moon, and in particular at the polar regions could obtain very high resolution maps And also because it's an active instrument that carries its own illumination source, it pulses a laser and measures the return. It doesn't matter really if you do that on the sunlit side or the dark side. And so what's nice is that you can then map the whole polar region with no bias and no data gaps in the permanent shadow. So here you can see a context image, I guess, of the topography of the South Pole. This is Shackleton crater here, and for reference, at about 20 kilometers wide. And the South Pole of the Moon is exactly right there on the rim. And so you can see there is a very high standing sort of massif that is composed of some of the rims, and also this that connects to Shackleton and the Gulash. And so from that, we can actually simulate by modeling what is the illumination of the ground. And so that needs to take into account a much wider region, because sometimes the obstacles, the part of the terrain that's blocking the sun can be hundreds of kilometers away. Even though the moon is quite small, there is a lot of topography. The maximum difference between the highest point and the lowest point at the moon is about 20 kilometers. So you can still see the horizon pretty far away, especially from those high standing points. So you can see that there are regions here in black, and that means they never get sunlight. So those are what we call permanent shadow. And also you can see on the rims, especially those high standing terrains, you can see pretty thin lines that are a lot brighter. And now if I bring this into a false color, you can see here when you see the red color, it means that you have more than 50% of the time you can see the sun, which is a little bit unusual for the polar regions. And as I said, everything that is exactly zero, no illumination, that is what we have named the permanently shadow regions. And so those are one of the points of why we want to go to the South Pole. You can see that close by to some places that have pretty good illumination, we can find some of those craters that never ever see the sun. And because the moon lacks an atmosphere, there is no heat conduction through through what's above the ground, and the lateral heat conduction, it doesn't perform very well. And so you can maintain gradients of temperature that are very high over very short distances. So except for scattered radiation and scattered thermal radiation, which can happen in a cavity like a crater, there is no heat source at all for the points that are in permanent shadow. And so that makes them quite cold. And some of the coldest temperatures measured in the solar system are actually on the moon. So this was also measured directly by the LRO Diviner instrument, which is a thermal infrared emission spectrometer and mapper. And so they measured, the whole moon, but here focusing on the South Pole, you can see some of those temperatures are well down below 50 Kelvin in sort of the purple tones. And also you can see the stability temperature on the surface of different compounds. And so you can see water here is at about 110 Kelvin. So everything which is darker than this shade of blue here is actually can host surface ice. Surface ice would not sublimate away. It would take 1 billion years to sublimate maybe like a millimeter of that. And so those regions are called cold traps, and they are typically about the size of the PSRs, right? So the permanent shadow regions. That's why we sometimes talk about it interchangeably, but they're not quite exactly the same. And also what's interesting, once you have access to the thermal data, you can see that it's not just water. There is a bunch of other interesting molecules that could be used for exploration as well. That can be exciting. So another line of evidence was, again, from Lola, so different measurements. So Lola measured primarily the topography of the moon, but he also measured reflectance of the surface. And what was interesting is that because, again, it was an active instrument, the reflectance of the surface was measured with zero phase. So basically, ingoing and outgoing rays are the same direction. So there is no phase angle between the two. And that means that there is no self-shadowing and all those complicated parameters that can enter photometric function. And basically, maybe you've never seen this image of the moon. You're familiar with the near side, of course, and the far side. But typically, when we look at the North Pole or South Pole, there's a lot of shadows that come into any mosaic you do. That's just the way things go because we have permanent shadow. But here you can see even the permanent shadow is not dark because we could see it with the laser illumination. And so that's great in its own sense. But what we did here was also look at separating the data between what is in permanent shadow and what is not in permanent shadow. And you can see there is a statistically significant difference between the two, indicating that typically permanent shadow regions are actually brighter than the normal moon. And so that led to the idea that potentially in some of those, or on average, in many of those, there could be some surface frost. The question is, this is seen at 1064 nanometers, so about 1 micron, but does it apply to other wavelengths? And also, this is just a reflectance measurement, so it's not really indicative of what is causing that. It could be, there's also proposals that this could be porosity, for example. So one of the nice things that you can do is look at spectroscopy, meaning looking at the same place on the moon with the same conditions, as geometry conditions, but looking at two different wavelengths. And if you can do that, and if there is a signature of, for example, water ice in the two wavelengths that you're looking at, you can see, you basically can get evidence for water ice, even if you don't have uniform illumination throughout the whole region. So here on LRO as well, there was an ultraviolet mapper called LAMP that was looking at much shorter wavelengths. So LOLA was about 1 micron, and this is looking at 0.1 to 0.2 microns. And there is here a very strong increase in the water ice reflectance between what is called the on band, when we have an absorption band, and so the reflectance of the surface is very low if it's ice, and the off band, which is more like typical terrain, and in that case the albedo is significantly stronger. And by looking at the ratio between what you measure the albedo, the reflectance to be off band to on band, you can see evidence for that ice. And so here, this is that study by Hain in 2015 that looked at that off to on albedo ratio. And when the number, when the ratio is high, that means that you probably have, some fraction of water ice that is in the mix of what's at the surface. So that was another line of evidence from LRO. Another one that was actually not coming from LRO, but from another infrared, this time spectroscopy investigation. So this one looked between 1 and 2 micron, and also was looking at specific absorption bands for water at 1.3, 1.5, and 2 microns. And what you can see is that you can see here on the right also the places where they detected surface ice. And so this is quite a different wavelength, but sort of same idea of looking for, in the same exact observation, looking at variation between different wavelengths that are consistent with spectral signatures of known species like water ice. But when you flip between the two, you can see that they don't necessarily agree exactly. And so that's why, as I mentioned, there's still a bit of still some ways to go to fully understand the story of ice on the moon. And so that's why we want ground truth, as I mentioned with Artemis. We actually have one point of ground truth, which is the LCROSS impact experiment. So LCROSS launched on the same rocket as LRO, but after LRO was off to the moon, LCROSS and its shepherding spacecraft was still attached to the Centaur second stage, and basically carried it once more around the Earth-Moon system to gain speed and basically impact the South Pole. So they impacted in the Cabeus crater, and there was about, I forget, 30 seconds or minutes time difference between two impacts. And so the spacecraft in the back could use its scientific instrument to look at the plume that was created by the impact and looking at the different species. And so that gave us a single point of ground truth, but very useful. It uncovered that there was indeed some ice in the sort of shallow subsurface at Cabeus, and also other volatiles that may be, again, useful for understanding where those volatiles come from scientifically, right? So which source could have produced those, and also for exploration in terms of in situ resource utilization. So NASA is continuing to try to understand this story scientifically, and the Viper mission, which is launching soon, will actually land in the South Pole region of the moon, and then throughout several months, we'll go in and out of permanently shadowed craters, pretty small ones, but still conducts experiments across transects to really understand the distribution of ice in the subsurface and how thermal environments and in situ ground truth of volatile distribution relate. So now I'm going to turn to another part, which is how special the South Pole region of the moon is in terms of sunlight. So we were looking more at the lack of sunlight, what creates very cold temperatures, what can cold trap volatiles and help us understand the moon and the moon system. Now we're going to look at something at the opposite end. So again, same image as before, just for context, the Shackleton crater that I mentioned, the South Pole here as a star, the Dergolash crater, and the connecting ridge, what we call the connecting ridge. So here is a movie showing what a typical South Pole winter season looks like. So the movie started exactly when the sun subsolar latitude went at the equator, and is going to follow, for about 6 months, where the sun subsolar latitude is going to increase to its maximum at 1.5 degree north and go back down to 0. And so you can see that sometimes almost the whole region is completely shadowed, and you have extensive regions of shadow, contiguous shadow, and only a few very high standing mountains and regions are shaded, right? So this is the winter season at the South Pole. If you look at the history of subsolar latitude versus time, this is sort of this star here at the this star here at the top. When the latitude is maximum, so at the south, that's the winter. So now the next slide here shows you the opposite. So now we're looking more at the green region, where the South Pole, the sun is moving from the equator to its minimum latitude and back. And so here you can see that as that goes, and here we're soon going to hit 1.5 south, which is the maximum of the sun position in the sky. So here now we see very extensive regions of sunlight, and basically, it looks almost like a different place on the moon. And so, you may think that the seasons on the moon should be a lot more subtle than on the Earth, because the tilt is only 1.5 degree compared to 23 degrees on Earth. But because of all that craft topography, the lack of heat conduction through the atmosphere, it's actually a very stark contrast between winter and summer. So as I mentioned, with the LoRa data, the topography data, we can simulate pretty accurately what is the illumination conditions at any time. And from that, we can draw, make averages over several years or decades. And so this, again, shows the same as I showed before, where the color scale here goes from 0 to 50% of the average solar illumination throughout, a pretty long baseline. And so now I'm going to show what happens if you held the sun at its minimum latitude, meaning that you held it all around at low longitudes as its maximum declination for the southern summer solstice. And so here you can see what I was talking about before, that significant part, for example, of the Shackleton wall here is shaded for most of the time. And when you look at the opposite side on the winter, a lot of the regions is basically in permanent shadow. I mean, we don't call it permanent shadow, we call it a seasonal shadow. But those regions will not see the sun for 6 months every year. And so that's an interesting thermal environment, as you can imagine. And this is what the Divine instrument has measured and split that data basically between different seasons. And you can see, again, that there is a huge difference in the thermal environments between summer on the left and winter on the right. And so looking now more from the perspective of going on the ground, you of course, at least initially, when to make things easier, solar power is very efficient, and so places that are very well lit of prime interest to be able to land and have enough power to do what you need to do. So here I highlighted on that average illumination map the places that have illumination between 25% and 50%. And so this, as you see, is a pretty small fraction of the surface. And you have to remember that for Apollo, like I was saying at the very beginning, Apollo and even up to 60 north, typically you'd be very close to a 50-50 ratio. So most of the surface here, if it was at the equator, would be basically red. And so that means that what's typical at the equator, what was typical for Apollo, where what we all think of as the moon from the ground, is actually very special at the South Pole. And when you narrow that color scale even further from 40 to 60%, you can see that it's actually an even smaller fraction of the surface. But now, as I said, this color scale goes up to 60%. And so that means that there are some places that actually see more than 50% of illumination. And that's what makes them so interesting. So looking at the same data, but now a little bit as a cross-section versus latitude. So I highlighted how much of the surface is sunlit on average 40% of the time at different latitudes, right? So you see that when you're at 55 or 60 north or south, at 60-degree latitude, about 90% of the surface is illuminated more than 40%. And it's not quite 100% because you always have mountains and rough topography. So there's always something that's going to shadow some parts of the moon more than others. And so the early morning or late evening are going to be shorter. But that trend, because of that, the fact that the sun is going to go lower and lower in the sky, that those obstacles of topography around you are going to become more and more important. And you see that, so that ratio of how much of the surface sees, typical Apollo conditions falls off very rapidly as you get closer to the pole. And so when you're in that 84 to 90-degree region, which is the Artemis, overall Artemis region for the Artemis missions, you see that you're below 20% typically. But when you zoom in at the bottom, now I'm going to draw your attention to the other two lines. So the blue line is what, exactly 50%. And so you can see that actually that stays pretty constant. Those are more like the high-lying areas, the mountains. And the most interesting one is the yellow line, which is that one where you have more than 60% of illumination on average. And you can see that that line is basically exactly zero everywhere on the moon, except when you get really, really close to the pole. And it still forms a very small fraction, right? 1% at best. But it's non-zero, and that's why the South Pole is a very special region. So why is that? So now narrowing in on just two areas on the moon, 2 points on the moon that are, I think, on the connecting ridge between Shackleton and the Galash, you can see why. So those are high-standing topography with you're several kilometers above most of the surface. So you have some obstacles around you from that ridge that you're on. But other than that, you have a very clear view of the horizon. And so most of the horizon is actually below 0 degree of your local sort of a flat frame. And so when you look at the path of the sun in summer, which is, those lines represent as you go around, as the sun goes around you, which is sort of that azimuth direction. In the summer season, the sun never gets hidden by the topography. In the winter, it does, but only for short intervals. So some of those darkness periods are only a few days long. And so that means that if you were to build a base there, or have to build, size up solar arrays and batteries and everything, you need to survive only those durations of several days, instead of having to survive basically, especially in the winter, at least 14 days, but maybe many more than that. And so that's what makes the South Pole very tantalizing, is because you can take advantage of summer days that are, hundreds of Earth days. And in the winter, you can basically survive the winter with much less resources than you would need at the Apollo sites, for example. And so, so that was just looking at 2 points, but now I'm going to look at a couple of illumination metrics. So one of them is how long is the sun in the sky above the surface in the summer, right? So as I said, I can go to very high numbers, but so this is, once you start going above this latitude, when the sun starts going above that point, in the spring, it will only rise afterwards, come back down. And so when does it hit that again? And then the other one is how long is the longest darkness period, right? And so now this is a map of the connecting ridge. So you can see that it's a 2 by 2 kilometer area. So pretty small, but you can see that you can have contiguous periods of sunlight of more than 200 days in several locations. So that means that if you land there in the summer, you'll have no problem, no night, and basically you can do exploration 24/7. And on the right, you can see the longest period of continuous darkness. And so I maxed this out at 14 days, which is the typical Apollo number. But you can see there's some regions just along the top of that range which go to numbers of 5 or 6 days. So again, that means about a third of the resources in terms of, for example, batteries that you would need compared to a normal Apollo type mission. And so that was at 2 meters altitude, these calculations. But if you go a little bit higher, for solar panels, and then those regions sort of just increase. And so that means that, depending on what, how big you're thinking, that opens up even larger sort of real estate. And so, yeah, those are what we call oases of light. And so those are interesting and potentially good places. And one of the questions that came out was, how can we connect them? Right? Those are very, very small, very localized. And here in the maps and the movies, I didn't point them out, but those, those are the 4, for example, that we highlighted here. But those are pretty distant by tens of kilometers. And so the question was, can we really, do we need to commit to just one, or can we travel between them? And so that was one of the questions. And because you see that in the winter, for example, mostly it's darkness between them. So you probably want to hone in, stay in one place, survive the winter, and maybe in the summer seasons is when you can travel. So this is the question we looked at and came up with proof of concept sort of trips that would happen going here from the connecting ridge to the Gerlache rim. But you still have to avoid the shadows, right? And so, as I said, the whole region experiences very complex shadows throughout. And so that the challenge here was to find trips that were realistic in terms of time-driven, recharge time and such, and still be able to connect the two. And you can see sometimes you're chasing just after a shadow comes out. Sometimes you stop ahead because there will be a shadow. And so that shows you the way to, and on the right, you can see the way back where you have to stop at specific points, wait in sort of those islands of light, and then continue your trip when things open up. And so what this found, so this proof of concept has some assumptions, minimal assumptions to try to see how minimal resources could be able to do this. But there may be better ways of doing it if you can, for example, drive through shadows and such. So those trips took, typically take 10 to 25 days, and mostly because you have to wait for the sun to turn to be able to cross shadows that were, what was in shadow before, to wait for it to basically be sunlit. So that was one proof of concept between Shackleton Rim and the Gerlache, and I'm just going to show quickly the same thing between the Shackleton Rim and a peak near Slater, which is on the right, which is also a place with high illumination. And so you can see sometimes you stay in place for quite a while until the conditions ahead of you are good enough for a drive. Okay, and the last movie, going back. And so, yeah, that was the idea. Can we travel during the summer seasons, and in the winter seasons, we would probably need to be at one of those points because not many points at the South Pole have a high illumination in the winter. Okay, so yeah, just to summarize this, I think I'm running short on time. So we sort of think it that way as a hibernation or winter season and a traverse season to be able to connect them. So I'll skip that. So in summary, I hope I was able to show you that the South Pole is an exciting region. It's home to both cold traps and highly humid terrain. And so that will provide a wealth of scientific opportunities to understand volatiles, how they got in placed, and how they can be used for sustained exploration. And conversely, the oasis of sunlight can support long-term presence by reducing resources needed and also to establish multi-year presence. And so those places have very long summer seasons, very long summer days, and they also have typically abundant solar power. So again, the Artemis missions are going to be very exciting to explore this unique lunar region. So I invite you to stay tuned for many discoveries. And again, thank you to the NASA Night Sky Network for inviting me and be able to talk to you. So that's it. Thank you.
Right. Well, thank you very much. This is really interesting. And we do have a few questions. And so let's get right to them. And if anyone has any other questions, please go ahead and enter them into the Q&A. I want to start off with this one. You've talked a lot about the amount of sunlight that you get there. Maybe you could, say something about the range of temperatures at those locations. Of course, there's no atmosphere to measure the temperature, and so what kind of? So we're just talking about ground temperatures, and what are we talking about for that?
Yeah, maybe the best is I go back to one of those maps of. So this is the average temperature, which is more indicative of the subsurface temperature, really, because it's the temperature of what would be basically at about a meter depth throughout the year. And so those are maybe a little on the low side, but the sunny terrain on the moon at the lunar South Pole is going to be colder than the hottest terrain during the day at the Apollo site, at the equator, because this solar incidence is going to be smaller. But the faces of crater that have, like a 30-degree slope will still get hit by the sun much more efficiently. And so those can still rise to about 350 to 370 Kelvin. It's just we probably won't see, numbers like 420 Kelvin like we see at the equator. So it still will be pretty hot. And so you still need to guard against the heat and guard against the cold, right? So if you travel in the cold, very quickly, it will go below about, 200, 250 Kelvin very quickly. And so, yeah, I hope that answers this question. Yeah, so you'll see extremes, but not necessarily much worse than what you would do at the equator if you stayed through the night. And when you travel to those coldest regions, right, the PSRs, those can be very challenging because those are cryogenic temperatures. So at that point, you're at 100, 120 Kelvin. And so those, that's a whole different issue. And so the Viper mission, for example, has been working on that, on how to operate at those temperatures. Have enough battery charge to be able to survive that. And after a certain time, you have to go back and recharge because you've drained your batteries, especially if you're solar powered.
So here's an interesting question along with these travel locations. What's the anticipated terrain along those rims for travel? What's the geological interest in the rims, or is there any?
Yeah, that's a good question. So so those traverses I showed, let me go here, for example, those traverses I showed, those were found by looking at the slopes, at the terrain, at the illumination. And so they do take into account sort of a traversable slope of less than 10 or 15 degrees. And that's at the 20 to 50 meter scale, right? So we don't have great meter scale data topography for everywhere on the moon. So that we're working on that for those specific regions where we intend to land. But I think those will be traversable. And in terms of geology, when you see for example, here, the little dot stop, there's usually sunny terrain right next to it. And so when you stop for several days at a place, you probably could do a lot of great investigation just around that while you wait to continue. The moon is going to be interesting, everywhere. So I think for the geology, the rims of the crater, for example, are very good as well.
Kind of sticking with the logistics of getting around, how do you get from the sunlit regions up there on the rims, which are the desirable places for people to be and stay, to the permanently shadowed regions where the water could be found? Because that's kind of the big goal, is to investigate those regions, right?
Yes. So that's a good question. So the first stage of exploration is going to be on smaller scale PSR. So here you see a big 20-kilometer scale PSR. So with 36 degree slopes going down the crater. So those are extremely challenging, and those will not be the first one that we go to. The first one we go to, maybe, let me back out. But yeah, maybe showing here, some of the small craters that are still, a few hundred meters tens to hundreds of meters. Those are probably the craters that are more accessible right now with, the sort of, not the first mission, but, the mission that will come after. I don't think the first mission will go into a PSR, at least I don't think that's the plan currently. But, follow-up missions may be able to do that. And as I said, the Viper mission will land a little off that map there to the top right. And they also intend to go into some of those, smaller craters. So the very large PSRs that may host volatiles, right? And those are some of the coldest ones. Those, at this point, may be explorable with sort of what we call hoppers. So, you land at a place that can be a long-term base, and then you go do another rocket boost to land there, and then you come back. So that's maybe doable in the sort of near term, but still quite risky. So I'm not sure exactly when that will happen. But the exploration of the very large scale PSRs is not in the plan currently, as far as I know.
That actually kind of brings up an interesting question about, if you want to explore, because they're basically, and I think that you mentioned this, they're using solar cells probably on their rovers or their facilities that they're living in. And so if you go down into these craters, you need to have a different power source because you're not going to be able to recharge your batteries. And so has any thought been given into what sorts of power sources that they would use? Would they because probably the thermoelectric ones powered by plutonium, like what the rovers have, probably doesn't generate enough power to do much, I suspect.
Yeah, so I mean, Viper is solar powered, right? So they won't be able to operate long term in the PSRs, but sufficiently to execute their science investigation. So they stand in the sun until they're ready, and then they go in the PSR, and the thermal design, I think, has been optimized to maximize how long they can stay in the PSR. But obviously, at some point, they need to come back, right? So that's doable, and that's probably the most realistic right now. In terms of, sort of nuclear type energy sources, one issue is the availability of that, right? And also, especially for crewed missions, do you want that with a crew? But also, especially in the PSRs, right? We're trying to go after volatiles that have been kept cold for like billions of years, and bringing the RTG may disturb that environment significantly. Even just bringing a rover, which is room temperature, is probably a challenge. So bringing an RTG source, will bring its own questions, right? Obviously, it can be very good for long-term presence and staying longer in the PSR, but it will also disturb the environment by adding a very significant heat source right next to places that are really, really cold. So it's a challenge, yes.
The goal is not to go down there and actually warm up the ice enough that it starts melting. Which actually was kind of a question, and we're getting close to the top of the hour, so we'll go for just a couple more questions here. In the perpetually cold crater bottoms, how cold does the ice need to be so that the vapor pressure is essentially zero, so it's not sublimating?
Yeah. Well, the number changes by a few kelvins depending exactly what source of data you use, but I think typically about 110 Kelvin is a number I've heard, where if you're below 110 Kelvin, you basically would sublimate less than 1 millimeter of ice over a billion years. So that's, a measure of being stable over long term.
And this is kind of an interesting question about the purity of the water in the craters. Will any impurities make it difficult to use the water for rocket fuel or other uses? I guess the thought is about the engineering that has to go into, actually utilizing the water resources that they're finding.
Yes, and that's a very important thing that many people, but not me, are thinking about is, in terms of prospecting, and that's what Viper is doing in part, is to try to see, okay, we have evidence from the orbital data that there is, hydrogen, water, ice on the surface or near subsurface. What form is it in, right? There's still a big question. How mixed is it with the regolith? Is it, intimately mixed, or is it like chunks of ice next to chunks of regolith? These are not known currently. And so some of those first missions, and also the crewed missions and the future robotic missions that are coming up, from the commercial lunar payload services. All those are going to try probably first to see what is the state of the ice, because I don't think we show yet.
Okay. And this is going to be the last question. I like this one. How is the South Pole different from the North Pole on the moon? We've talked a lot about the South Pole. Presumably, some of the same conditions exist there as far as the amount of sunlight. And so why are we focusing on the South Pole and not thinking about the other side?
That's a good question. The two poles, actually, when you look at the topography, look a little different. The North Pole has more smaller craters that are embedded within pretty large flat basin scale. I mean, not large impact craters. Whereas the South Pole has a lot more rough topography. So some of the coldest temperatures are actually mostly in the south. The north is interesting, is on the right, and also the north, because it doesn't have those peak place exactly like what the south has. It doesn't have those very interesting places for exploration that have very short winter nights and very long summer days. Those are much rarer at the north even. So I think that's part of that. But yes, the north has similar conditions, maybe not as extreme temperatures, but still enough to cold trap volatiles. And so yes, it's probably, the story is hopefully not too different between two poles, but the South Pole has a couple of very interesting locations and maybe something a little different.
All right. So something for the next batch of missions, I suppose. So it's a big moon and there's a lot of places to go there. So.
Yes.
All right, well, that's all for tonight, everyone. Thank you, Erwan and Andrea, for joining us this evening. And thank you, everyone, for tuning in. You can find this webinar along with many others on the Night Sky Network YouTube channel. Join us for our next webinar on Tuesday, October 26th, when Dr. Karina Alden joins us to tell us about space weather and how it is analyzed and forecasted. So keep looking up and we'll see you next month. Good night, everyone.
Before everyone goes, I just want to take a moment, Brian, to thank you for all of your webinars that you've hosted over the years. This is Brian's last webinar for a little while with us until we drag him in for maybe helping us at some point. But Brian has been with us hosting these webinars since 2016. And I think you said maybe over 80 webinars at this point that you've hosted. Thank you, thank you, thank you. Kat is going to take on the next steps of this, and we'll be hearing more from her next month. Thank you all so much. Really appreciate it, Brian.
Yeah, it's been a lot of fun. And unfortunately, the two eclipse projects that we are going are just demanding all of the time. So something had to give. So unfortunately, it was this. So.
We'll rope you back in one of these days. I hope so.
We'll think of it as a hiatus.
There you go. Thank you, Dr. Mazarico. That was just wonderful.
Yeah.